Okay, good morning. So we continue the lesson. This lesson is not actually a lesson. There are a lot of examples. We want to go through them. Not a lot of examples, but some examples that we haven't gone through them. So might be it's a good idea if I, for example, show you the problem here. How many permutations of the numbers 1, 2, up to 9 are there such that no two of the numbers 1, 2, and 3 are adjacent? Yes. So we want to see how many ways we can arrange numbers from 1 to 9 in a row, but there is a constraint. I don't want to have the situation that 1 is adjacent to 2 or 1 is adjacent to 3 or 2 is adjacent to 3. I just want to take them off and I want to see how much is left. Or anyway, is the question clear what we are supposed to do? Yes, okay. So I want to wait a little bit for you because this problem is actually could be hard, or there is also a simple trick for doing it more efficiently. So I just want to wait for you to see how you think about the problem yourself. Okay, any ideas? This problem is simple if I just tell you two of them shouldn't be adjacent. But let us review, by the way. Okay, I can let me add a page here. Let me try to review a little bit about what we learned before. So let us assume that I give you these 9 numbers. This is not the main problem. This is not the problem that we are supposed to solve. But let me give you just one feeling. 1, 2, 3. Let me also change this pen. 3, 4, and up to 9. Yes? So let me ask you this question. We had this question before. I just want to see how many of you remember what to do. Yes. Let us say that if I ask you how many permutations are there, this is extremely simple. How many permutations are there in total? 9 factorial. Now, if I ask you in how many permutations 1 and 2 are not adjacent. In this problem, this new problem is harder than what I'm talking about right now. This, in principle, you should be able to solve it. In how many permutations of these objects 1 and 2 are not adjacent? In principle, you should be able to solve this very simply. We had similar examples before, not with numbers, but with people. 2 people hating each other. Do you remember I told you that if you have 9 people, they want to make a queue line, and 2 of them, they don't like to be next to each other immediately, we should be able to solve that problem rather easily. What was the topic of the lesson? Do you remember?
The formula.
No, the name of the. So there we had 3 rules. Yes, the product rule, the sum rule, and
Division kind of rule.
you're inventing new rules now. Yes, no.
The
Complement rule.
Yes.
Yes, that was the complement rule. So one way of solving this problem is using the complement rule. Let us just review. It seems that you have forgotten a little bit. Okay, so the total number of, I don't know why this iPad is acting weird. Okay, so in how many ways I can arrange them? The total number number of permutations is how much, as you said? Is 9 factorial. But I don't want to have 1 and 2 immediately next to each other. So one way to think is that let us count the number of permutations in which 1 and 2 are adjacent, and then take it off from the total number. So what is left is the number of permutations in which 1 and 2 are not adjacent. Is that right? So, but now help me. In how many permutations 1 and 2 are adjacent? So this means that do you remember the idea of having books of the same topic or something like that? You put them in a bundle and call them object, I don't know, let me call it object A. And then if I ask you how many objects you see, you have one object A, and then 3, 4, up to 9. How many objects you have? 8. Yes, I have 8 objects because 3, 4, 5, 6, 7, 8, and 9. 1, 2, 3, 4, 5, 6, 7, and one object A, 8. Yes. So now I want to count the number of permutations. Permutations having 1 and 2 adjacent. Yes, if I ask you how many of them are there, you should be able to answer them. How many of them are there?
8.
8 factorial, yes? So 8 factorial, but 8 factorial is not complete.
Times 2 factorial.
Times 2 factorial, because when I say 1 and 2 are adjacent, sometimes 1 comes first, 2 comes second, or 2 comes first, 1 comes second. So you multiply that by 2 factorial. And the question mark will be what? 9 factorial minus 2 factorial times 8 factorial. Yes, this is the answer. By the way, let me simplify this because I want to compare it with a different method. So instead of 9 factorial, what can I write? I can write 9 times 8 factorial, but 2 factorial is simply what? 2, and times 8 factorial. And then what I do, I factor 8 factorial out. It becomes 9 minus 2, but what is 9 minus 2? It's 7, so it becomes 7 times 8 factorial. So that's the simplified version of what I want to do. But can you find another strategy to solve the same problem without using the complement rule? Okay, if you learn this, then we come back to the harder problem that we started with today. Can you only use the product rule to solve that problem? Because, by the way, do you agree that this way I did it is natural? I don't know, for our human brain, it works like this. We say that, okay, I want them to be not close to each other, so let me count all the number of possibilities, take them off, then take those items that they are close. So this, I don't know, this is somehow comes to our brain more naturally than the one that I want to describe. But can you find another way to solve this problem? It's a nice technique, actually. Okay, let me describe the technique for you. The technique is that for the time being, ignore these two, and let us arrange numbers from 3 to 9 in a row. Okay, but with, you can imagine that you have enough space between them. Okay, so for example, what I do, I will take some positions. I would say, let me make it simple. So I would say location number 1 and location number 2, okay, and location number 3 up to, how many of them are left? I have 9 numbers. I take 1 and 2 out. There are 7 locations left for me. So I would say that location number 7. Yes. Okay, so what I want you to understand, so let me, by the way, write location number 6 and then location number 7 to highlight some point here. Okay, so these locations are supposed to be filled with numbers 3, 4, up to 9. Okay, in how many ways I can do that? How many ways?
Sorry, can you repeat?
So I want to fill up these locations. I momentarily ignore numbers 1 and 2 that I have some constraint on them. Forget about them momentarily. What is left for me? 3, 4, up to 9. I say that, okay, forget about 1 and 2, arrange 3 up to 9 in a row. In how many ways? You need 7 locations, so 7 factorial, okay? So you get 7 factorial. If I ask you what is this 7 factorial, you will tell me this is the number of permutations of these objects in these locations. But now I go and take my 1 and 2, I distribute them here, but So let me tell you something. So let me highlight this again. So I will take this one, a box, another empty place here, okay? And then I have another empty place here. Yeah, you have to be a little bit patient to understand what is going on. And then I have another empty place here. So do you agree that, how many empty places are there, first of all? How many squares do you think, if among I start with a box and then a circle, then a box, then a circle, then I continue until the very end that I have a box at the very end. So how many boxes are there? Can you tell me? Yes, Abdul? 8. Yes, there are 7 places. I fill them up. So if you, do you agree that there are 8 boxes?
Yes.
But do you agree also that if I choose 2 of them and fill them with 1 or 2, I reach to my goal? Yes, because for example, let us say I choose this one and that one. Sorry, I choose this one and that one. I put 1 here, 2 here. Then 1 and 2 are not adjacent because there is something between them. Or you might say that I can take this one with that one. I put 2 here and 1 here. Then again, 1 and 2 are not adjacent. So this is a very interesting way of looking at the same problem. Okay, so this means that how many locations you have? 8 locations. They are distinct. But how many objects you have? 2. You want to put 2 objects in 8 locations. That is the previous lesson. What was that? Pn of r. N is the number of objects or locations depending on the situation of the problem, and r is the other way around. Yes, in this case, what should I write? So I would say that there are 7 factorial ways that I can fill up the circles. After that is done, I have 8 squares. I want to pick 2 of them and fill them up with 1 or 2. Okay, in how many ways I can do that? As the previous lesson tells me, it is a P of what and what?
8 and 2.
Yes, 8 locations and 2 distinct objects. And then what should I do between these 2 numbers? 7 factorial on one hand and P of 8 and 2 on the other hand. Multiply, yes, because I do this one first and then I go to the next stage, so I multiply them. This is also another way. So what I used only the product rule. Yes, let us confirm that this number is really the same number we got in the previous method. So how should I confirm that? Do you remember the formula for P? Let me repeat it here. So the formula of Pn and R is equal to a fraction. The numerator is filled with n factorial. The denominator is the difference factorial. Yes? So that was the formula that we had in the previous lesson. Okay, so now, by the way, in exam, it is enough if you write it like this, that's okay. But here I want to compare these 2 numbers to see that they are really the same. So let us do that. So what should I do? 7 factorial, let me copy and paste 7 factorial. But instead of P of 8 and 2, what can I write in the numerator? 8 factorial. What should I write in the denominator?
6 factorial.
It's the difference between these 2, which is 6 factorial. But I can simplify it a little bit more. Instead of 7 factorial, I can write 7 multiplied by 6 factorial. And then I copy and paste my fraction, which is 8 factorial divided by 6 factorial. And then what is happening? This and that are cancelled. So what is left? 7 times 8 factorial. Yes? And then you see that this answer exactly matches my answer here. So these are 2 different ways of solving the problem. Okay, so that's a review. This is the new method I want you to learn. Okay, so but I hope that you agree with me. The first method is hard to apply for now, the new problem, because in this new problem I do not have only 2 objects that I don't want to have them adjacent. I have 3 objects that none of them are supposed to be adjacent. So the complement method is a more complicated method to solve that problem. Okay, that's also fun if you want to consider all cases. We can talk a little bit about that. But I hope that you agree that this method more or less immediately applies to this problem as well. Yes? Yes? Okay, so let us go back now. Now let us solve this new original problem. So why, first of all, tell me why the complement method is not working as simple as before. So let me ask you this question. In how many ways I can say that I have 1, 2, and 3, 4, 5, 6, 7, 8, and 9. Okay, so let me consider the total number of arrangements, which is again 9 factorial. And this time, let me put these 3 in a box and take it off. Why do you think this is not correct? Do you understand what I mean? I want you to understand why the complement method, as I did for that problem, does not work here. If I want to use the complement method naively, as before, I would say that, okay, I have 9 objects, so there are 9 factorial ways to arrange them. And now let me put these 3 in a box and call it A. And then how many objects I have? 1, 2, 3, 4, 5, 6, 7. So it becomes 7 factorial. And then how many arrangements I have for 3 objects? 3 factorial. And subtract them. So this is mainly the novice students make this mistake. These two problems are not the same. I want you to understand. They are very close. I want you to feel this is a wrong answer. Why? Yes, Hussein?
So how did you get 7 factorial when there were 6 numbers?
That's a different question, okay? Because the object itself should be considered as well. The object that I put the box. Yes? So you spoiled everything, okay? Yes. Yeah. Why this method does not work?
It's because you can also have that 1 and 2.
Yeah, exactly. So when I take 1, 2, and 3 off, yes, it means that in the permutations left, this is not the case that 1, 2, and 3 are are adjacent. But it might happen that 1 and 2 are adjacent and 3 is not adjacent. Okay? This is not being considered in this method of complement because I considered all of them not to be adjacent. So this is why this complement method does not work. Is that clear? Yes or no?
Yes.
Okay. Now, but I hope that you see that the second method is more or less immediately applicable. Did you learn the second method? If you learned, just let us write that. Okay? So in the second method, let me write the numbers in front of you. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? So the constraint is among these 3 numbers. So, do you remember that trick? I told you that momentarily ignore these. Okay, and then how many of them are left? 1, 2, 3, 4, 5, 6 left. So how many locations you need for these 6 numbers? 6. No, so how many locations I need? L1, L2, up to L5 and L6, yes? Okay, so how many ways I can fill these locations up with these 6 numbers? It is very simple. So it is 6 factorial. But after I arrange them, there are some space in between them, so I can just draw some squares here for you. 1 square here, 1 square here, and 1 square here. We continue another square here, another square here, and 1 more square here, yes? These are the locations that if I want to, I can fill them up with 1, 2, and 3. And it doesn't matter, I don't need to be worried. In any way that I fill them up, they are not adjacent. Do you agree?
Yes.
Okay, so in how many ways I can do that? Then how many empty locations I have? Can you tell me how many squares you see now? 7, because there were 6 locations, then I have 7 squares as well. But do I need all of them? No, I need only 3 of them. So it becomes, according to what we learned before, P of 7 and 3. And then I multiply them. The answer of this is so simple. There is a method of using complement method for solving that problem, but it becomes very complicated. So this is the best way to solve that problem. Yes?
Can you always assume that there's one more box than circle?
Yes. Yeah, in these kinds of problems, yes. Any questions? Yes?
But should we leave the answer like that?
Like that, unless I mention you, I want you to find the answer. Yes? Because even if you want to calculate it, it's not that easy. You just, yeah. Any questions? Okay, so now let us go to the new example. Now you have a little bit of experience of these kinds of problems, so let me read the problem for you. So how many permutations of the letters of the word international are there such that no two of the letters R, A, and L are adjacent? This is essentially the same problem. From today's lesson point of view, but let me not spoil the problem, wait for you, okay? So we have the word international. How many letters are there, by the way, in international? So let me count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes? So there are 13 letters here. You want to start permuting these letters and creating new words. But there is a constraint. None of the letters R, A, and L are supposed to be adjacent. Yes? We want to see how many ways we can do that. Do you have any question or want to answer?
Yeah, I just have a question.
Yes.
So this would also mean that since there's two A's in the word international, A and A cannot be also adjacent, right?
No, A and A can be adjacent.
Okay.
Yeah, because my constraint is only about R, A, and L.
The constraints are just in relation to the letters, not the letters themselves.
Yeah.
Okay.
And I always told you that we use the convention. So in this word, there are two letters of A. So you should use exactly two letters of A. And if I have, I don't know how many letters of N, for example, it's 3 of them. So you have to use exactly 3 N's. Okay. Do you have the idea? The idea is exactly as before, but the only difference is what? In the previous problem, we didn't have any repetitions, but here we have some repetitions. But I hope that you remember how we could solve the permutation with repetition before, yes? So if you didn't remember that, then you are a little bit in trouble. So if you remember, I will actually write them in this way. So I would write international, I have I, N, and then I have T, and then E, R, but then I have again N, and A, and T, I, O, another N, and then A, and then L. So let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's correct. I hope that I haven't missed anything. Okay, but you see that the constraint is on L, A, and R. They are not supposed to be adjacent. None of them is supposed to be adjacent. So what should I do? I take L, A, and R out. Okay, so how many letters are left for me? 9. Okay, so how many locations I need? I need 9 locations. So I would say that, okay, I have location number 1, I have location number 2, up to location number 8, and finally location L9, yes, L9. So in how many ways I can fill up these locations with letters that are not these letters?
9 factorial.
No, 9 factorial is in the case that I do not have any repetitions at all. But even if I take them off, you see some letters have repetitions, yes?
Yes.
So let me, highlight them. So these are the letters left for me. This box and these letters and these letters and O and E. Yes, these are left for me. R, A, and L of my. Okay. So I need to fill up these locations, these 9 locations with these 9 letters that I have highlighted here. So in how many ways I can do? If none of them was repeated, the answer was simply 9 factorial. But now I see that I is repeated 2 times, N is repeated 3 times. We had this before, do you remember? So I write 9 factorial, but I have to divide. Yes? How many i's you see? 2, so you divide by a 2 factorial. The reason this works in this way, we did it before, so I don't explain more. And then for n's, I divide by 3 factorial, but for t's, I divide by 2 factorial. But for e and o, if you decide, you can divide by 1 factorial, but that is not necessary because 1 factorial is 1. So far what I have done, I have put these highlighted letters in these locations. But then how many squares I need to consider? Then you know the trick. How many squares you need? 1, 2, 3, and then you have here. You can just continue, and then you have 10 squares, yes? Yes? Okay. And then you need to fill up these empty spaces with the letters that we have some constraint on them, which are R and 2 A's and 1 L. So how should we solve the problem now?
Is it possible to just write P of 10 4?
Is it? P of 10 and 4 has some constraint. The locations should be distinct. Yes, the locations are distinct, but the letters should also be all distinct. Otherwise, this will not work. But the problem is not that hard because just A is repeated 2 times. So if you write P, if none of them was repeated, so you would have written P of what? How many locations? 10. And then how many letters are there? 4. But this is not correct now. Yes, because this considers that A's are different. So if it replaces A, it will count it once more. But this is not correct unless
Divide? No?
Yeah, divide by
2 factorial.
2 factorial or 2, yes, because for any choices that are, for example, let us consider this formula considers the case that A's are different. For example, let me write something here. Assume that we put R here, we put A1 here, there is no A1, but this formula thinks that there is an A1 and A2, yes? And then we have letter L here, yes? The way that the formula thinks, if you use this formula for this situation, it means that you are considering that A's are different, yes? But in practice, A's are not different. So then it means that I have to divide this number by 2 because every location of A1 and A2 can also be considered with A2 and A1, which are the same, but this formula doesn't sense that they are the same. Okay, so you have to divide this by an extra 2 here now. Yes? Or as you want, 2 factorial, it doesn't matter. And then the answer is multiplication between these. Is that clear? Okay. So this technique is good to know about. If there are some letters that are not supposed to be adjacent, if there are 2 not to be adjacent, you can use complement rule or this trick, but this trick is also simpler if the number of objects with constraints is more than 2. Yeah, so this trick is good to know. Okay, so I want to wait for you again. Again, the same story of adjacent letters but in different problems. So how many 12 permutation of the letters of the 26 English alphabets are there such that each permutation contains all the letters A, B, C, and D, but no two of these letters are adjacent. Be careful, it is 12 permutations. There are 26 English alphabets. We don't want all of them. We want 12 permutations. But we still have more constraint. In these 12 objects, letters that I choose, A, B, C, and D have to be there, but they shouldn't be adjacent. So the constraints are more. So I want you to think about the problem yourself a little bit. Okay, any ideas? Before solving this as a little bit harder problem, let us try to review things. So you should be able to answer this question rather immediately. So how many 12 permutations of the letters of the 26 English alphabet are there, finished? So what's the answer? This you should in principle be able to answer quickly. No. 12 permutation. It means that I have 26 objects, but I don't want to use all of them. I just want to pick up 12 of them and then arrange them in a row in a way that order matters for me. 26 factorial is the case when I use all of them.
So 12 factorial?
No, come on. So I don't know. So how are you coming with me then? P of 26 and 12. This is the lesson we learned last time. So what is the whole point of P? In the case of n factorial is that I use all my objects. But if I want to choose a sub-collection of my objects and arrange them, that is the P formula. Okay? But in the P formula, the locations should be distinct and the objects should also be distinct. So if I just stop here, the answer to the problem is very easy. Of course, I'm not saying that calculation of this is very big number, but I just want to stop there. Okay, if you want, you can use your calculator to calculate this. Okay, and now let me make it a little bit harder. Okay, now we continue. How many 12 permutations of the 26 English alphabets are there such that each permutation contains letters A, B, C, and D? Now stop. How do you solve this problem? Don't continue. So ignore the last part of the problem. Yes? Yeah? So then what is the role of 12 here? Okay, so can you repeat again? So you say P of 22 and 8. Add. Okay. Okay. So the main mistake is probably you're making is adding. I'm not considering that this is true or false. We can discuss about that later. But when you do that, your job is still not finished. When the job is in, because your job is to have 22 items chosen. But so far you have chosen 8. Yes? So you need 4 more. So if you say add, it means that either I do it in that way or in the other way. There is no or here, there is and, yes? So this is important for you to understand that even if these answers are correct, you have to multiply them, not add them. This is important. But I don't think the first one was wrong. Yeah, so how many locations do I need? I am not solving the main problem. I am solving the problem up to here. Okay, so let me write it and then I will clean it here. So what you say that for 12 permutation, how many objects first of all I have? I have A, B, C, D, E up to Z. 26 letters. Yes? But I want a 12 permutation. A 12 permutation means how many locations I need? I need 12 locations. Location number 1, location number 2, location number 3, 11, and 12. Yes? I will clean this, we don't need to solve that. Okay, but now someone has decided 4 letters should be A, B, C, and D. Okay? And 8 letters is under my control. I will choose them. Okay, so how do you think about the problem? How do you think? So what you said is not wrong, actually. But so the number of items that you have is 26, okay? But 4 of these objects are A, B, C, and D. For 4 objects A, B, and C, and D, how many locations I need? I need 4. So first of all, I choose 4 of these locations and I arrange A, B, C, and D in the chosen locations. This is a standard problem. How many ways you can do that? How many ways you can do that? You have 12 empty spaces. Your objects are 4, A, B, C, and D. You put them here. So how many ways you can do that? Yes? P, 12, and 4. Okay? So far, 4 of these locations, say these locations, are occupied for A, B, and C, and D in some way. How many locations are left for me now? 8. 8 locations are left, but how many letters are left for me? 22. Yes? So what I need to do, this time the number of objects is more than the number of locations. I told you that P can be used in both cases. If the number of locations is more than the number of objects, or if the number of objects is more than the number of locations. So both of them appear in the same problem here. So what you do, you say that, okay, now I have 22 objects in my hand, which is 22 letters, but the number of locations left for me is 8. Yes? And then I multiply them. So what, Sarah, you said the first one is actually correct. Of course, you did it the other way around. It doesn't matter. Yes? So first you chose the 8 locations for 22 letters, and then you choose 12 for. Is that clear? Yes or no? Okay. So if I stop the problem up to here, this is the answer. But now let us solve the whole problem, the original problem. So we also have one more constraint. I don't want to have A, B, C, D adjacent now. Not only I want to use them all, but I don't want to have any of a pair of these numbers to be adjacent. So because this is not the original problem, so if you don't mind, let me just clean that and wait for you to see how it works. So how do you think about the problem now? If the letters are not supposed to be adjacent, you learn a tool, you have a trick in your head. So how should I use that trick in this problem now? Yes?
Is it again to like group A, B, C, and D under one like?
No, I told you that this method does not work for if I have more than 2 objects. It works. It is extremely harder to use complement rule. What I told you, do you remember what was the trick? If you do not want to have any of the letters adjacent, momentarily you ignore about those, and then you solve the rest of the problem, you get some empty spaces among them, and then you start filling them. Do you remember squares and circles I told you? So that's the same problem, so why don't you use it? Yes? So, okay. Let me just tell you. So for the time being, ignore A, B, C, and D momentarily. So how many letters are left for me? 22 is left. 22 letters are left. And how many locations I am I'm going to use now 8 locations because 4 of them should be reserved for these letters. Okay, so this means that I have 8 locations. Location number 1, location number 2, up to location number 7 and 8. Okay, and then ignore these 4 letters. Okay, so you have 8 locations, but you have only 22 objects. You want to choose 8 of them and arrange them in this row. How many ways you can do that? It's a very standard problem. What is the answer?
Sorry, may you repeat?
No. Yes, what should I write here? I want to fill up these 8 locations with English alphabet except these 4 letters A, B, C, and D. In how many ways I can do that?
Is it P of 22 and 8?
Yeah, it's P, 22, and 8. So it is P, 22, and 8. Pardon? No. It is by convention the bigger number should come first. But you can interpret the same number in 2 different ways. Don't get confused. It doesn't mean that in the other perspective you have to switch the letters, the numbers. So P22 and 8 can be interpreted in 2 ways. Either I have 22 objects and 8 locations, or I have 8 letters and 22 locations. But in any case, you do not write one of them 22 and 8 and the other one 8 and 22. You always write it as P of 22 and 8. Yes, but you can interpret the same number in 2 different ways. Okay, so this P22 and 8 is the number of ways that I can fill up these locations. Now assume that these locations are filled somehow with those letters. Now I want to bring A, B, C, and D in and arrange them. But I have another constraint on A, B, and C, and D. They are not supposed to be adjacent, none of them. So that trick that we learned in the beginning is useful again. That was the trick, I can call it the trick of squares and circles. I don't know, we can invent names. Yes, so we have these locations left for me that I can use them to put A, B, C, and D, yes? So how many squares you see? 9. But I do not need all of these 9s. I need how many of them? 4, because there are only 4 letters left for me. But it is guaranteed that in any way that I fill these squares with these 4 letters, they will not be adjacent. It is guaranteed there, yes? Okay, so what's the answer then? What's the answer?
P of 9 and 4.
P of 9 and 4, thank you. So I would say that the other part is P of 9 and 4. So you see, if you don't understand this trick, understanding where 9 is coming from is a little bit hard, yes? Because 9 has nothing to do, apparently, with this problem, yes? So this is the answer to this problem. Any questions? Okay, so now let us switch gears and then solve a different type of problem. So here, this is also in your book, some of them. So you are supposed to prove a formula. So there is no counting problem at all here. They are testing your skills in algebra and factorial algebra, yes? So you are supposed to prove this equality. The left-hand side is equal to the right-hand side. We want to show that. So what is your suggestion? So let me write a formula. Hopefully you understand the formula is needed here. Which formula? The formula for P of N and R. Which is, and by the way, this is also given in the formula sheet, so you don't need to remember that. So this is the formula I am going to use. So remember, the number that I put in the numerator is the first number factorial. And the number that I put in the denominator is what? The difference between these 2 factorial in the denominator. And then I told you before, even in trigonometry, in any lessons we had, if you want to prove equality, it is always better to start from the side which is more complicated and try to simplify it to reach to the other side. So in this case, hopefully you agree with me that the right-hand side is more complicated. So I start from the right-hand side. By the way, there is nothing very special here because that's exactly the same formula. So let me not explain anything. I just copy and paste the formula here. But for the second one, I want to hear from you. What should I write in the numerator? Can you tell me? This is P, N, and R minus 1. So this means N is still the same N. But instead of having R, what do I have? R minus 1. So what will happen in the numerator is again n factorial. But in the denominator, I have n minus r minus 1 in total. And then whatever it is, factorial. Is that understandable? Yes? Okay, then we continue. So I will not do anything with the first one. I just want to do a minor change in the second fraction. So I keep the numerator still the same. But what can I write for the denominator? A little bit better way of writing.
N plus 1 minus r.
N, yes, n minus r plus 1. Because that minus sign goes in, it becomes minus r plus 1. Okay, now I want to wait for you. What do you think I will do from now? Remember, your goal is to reach to the other side. And the other side is one fraction. Whatever it is just one fraction. But here, how many fractions I have? 2. I am adding those 2 fractions. My goal is to reach. Yes, Hussein? Okay, multiplying for the idea of common denominator is correct. But multiplying, it's always working, but it is not always comfortable to do that. You need to find the optimal common denominator. Yes, multiplication is of course always a common denominator, but that's not always the optimal one. So the optimal one, let me just rearrange this a little bit. So I copy and paste this first fraction. Yes. But for the second fraction, I write what? N minus r plus 1 multiplied by something factorial. Can you tell me what is that something? So you know that if I say 9 factorial, you can write 9 times the previous factorial. If I write 10 factorial, you can write 10 times 9 factorial. So what can I write now? N minus r factorial, yes. Do you agree? N minus r plus 1 times the previous number, which is n minus r factorial. And now you see that this itself will play the role of the common denominator, because this is divisible by itself and it is also divisible by that one. So this itself is the common denominator rather than multiplying them. Okay, so then what happens? I say that this one in my head divided by that gives me this factor. I have to multiply this factor by its numerator. So it becomes n minus r plus 1 multiplied by n factorial. Then I have addition here. So I put addition. So, but this is exactly the same denominator. So no changes is necessary for the numerator of the second fraction. Okay. Then what? Can you see what I'm going to do now?
You can factor out
N factorial. What can I do for the denominator? Now that I found the common denominator, I can put it back into the simplified version that it was before. Yes, because if I ask you what is this, you still can tell me this is exactly this expression. I don't need it anymore, so if you don't mind, let me write it in the more compact form. And as Gustav mentioned, there are two n factorials, one here and one there, I can pull it out. So what is left from the first one is n minus r, yes, plus 1. This is a little bit strange. That is not what I expect. So let me see. Yes, now I understand what I made a mistake. And you didn't inform me at all. There is one r here. Okay. So I put an r here as well, yes? That is an r here. And then this r will also go here. Okay. And then I have plus what? R now. So that was my mistake, sorry. I didn't see that r there. So I put an r here, and this r will repeat itself here, and this r will be multiplied here, repeat itself here. And now when I pull n factorial out, this is left from the first one, but r is left from the second. Yes, is that clear? Now this is now good, because this r now cancel that r. So what happens? I will get n factorial times n plus 1, and then divided by n minus r plus 1 factorial. Okay? Now, can you simplify the numerator a little bit for me? What can I write for the numerator? N factorial multiplied by the next number, because n factorial means 1 times 2 times 3 up to n, but you also multiplied by n plus 1. So how can you write it then?
N plus 1.
N plus 1 factorial, thank you. And then the denominator, I have n minus r plus 1 factorial. Yes?
Yes.
Okay, but do you agree that we are done now?
No.
But this is the left-hand side as well. Why? If you don't believe in that, let me ask you, if you don't like this method, so let me write the left-hand side as well. If I ask you to expand the left-hand side, how do you do that? N plus 1 is playing the role of n, and r is playing the role of r itself. So what should I write in the numerator if I want to write the left-hand side? It becomes n plus 1 factorial, and the denominator is n plus 1 minus r factorial. Do you agree?
Yeah.
Now look here, this is the simplification of right-hand side, and this is the simplification of the left side. Are they equal?
Yes.
Yes. So this means that the left-hand side is exactly equal to the right-hand side. Yes? Is that clear?
Yes.
Okay. But I don't like this method because we are working in combinatorics. It is better to have a combinatorial argument, which is extremely powerful in combinatorics in mathematics. So it means that without doing algebra, we should be able to prove this formula based on counting strategies. Okay, so I didn't plan to tell you this, but now I feel good about it. Let me just tell you, okay?